And I would like to thank the organizers also for inviting me to give this presentation. I would like to show you some of the recent work that we have carried out in order to try to speed up computation for metal forming processes. So this is a work that have been some of the main contributors of this work were former PhD students, Kofi Pozzo, Hugo Ripper, Mohamed Ramadan, Frédéric V, and it was also carried out in close collaboration with Hugues Digonnet, who is not working at Central Nantes. So first I would like to present the context of this work, which is metal forming, bulk metal forming. So sometimes people say that forging is one of the oldest manufacturing process, but forging is also a process that encompasses a wide range of shapes, of a series of productions. You can see here, for instance, small shapes and with small series. We can also move toward the car industry, the domain of mass production, and where, for instance, the production is about several thousands of parts per hour. It can be also a domain of very huge parts, for instance, for the tank of a nuclear power plant. And the recent history in France has shown how important it is to have a good prediction and a good manufacturing process for those security components. So numerical simulation is ever present in that domain since the last 2 or 3 decades. So it is used by technicians mainly, who use simulation to predict very complex flows, also to try to improve the geometry and to minimize the volume of material that is necessary to produce the parts. It can also be used to predict the tool failure and to improve the tool life. And just to mention here the different length scales that we may have in rolling, for instance, where you may have slabs that are several meters, 1 or 2 meters wide, but the accuracy that is looked for is sub-millimetric or sometimes micrometric. So it's a domain of production, so it means that people are expecting results within one night or within very reduced number of days. However, for some processes, I would call them incremental processes, we cannot reach these goals. And as you can see here, for instance, for rotary swaging, with the computational time, whatever the parallel facility, parallel optimization that we can use, we have computational times that are several days and sometimes several weeks. This is also the case for rolling. And so the main characteristic of this multipass rolling and the main characteristics of this problem is that the deformation is very localized and we have a very large number of time steps. So this is a motivation to try to speed up and to reduce computational time, which is always something that people are looking for. But in this context, we are going to try to use either numerical methods that have been developed in other different contexts, different field of computational mechanics, or develop new methods. So first, very briefly, I would like to present the skeleton of the equation that we are solving. So it's a problem of evolution. So we are using an updated Lagrangian formulation. The simplest conceived equation that we can use is a viscoplastic material, which can be purely rigid. We have a balance equation. We have the contact equation with friction. For contact is quite important. And we end up with a velocity pressure formulation. And due to the remeshing, the large deformation requires a lot of remeshings, we have to use a simple element, a tetrahedral element, and in order to pass the compatibility condition, we use a P1 plus P1 formulation, which means that the stabilization is obtained by introducing a bubble. Contact is enforced by a penalty method. So we end up with a nonlinear system, and we have to solve. We have an implicit formulation, so we have to solve several linear systems at each iteration. Simultaneously, we can solve the the heat equation with the Galerkin formulation, and we end up with a couple problems. And because we have very small time steps, and because the thermal coupling is not too large, we can use an incremental coupling, which means that we simultaneously solve the mechanical and then thermal resolution. Because we have a large system to solve, we are using an iterative solver. in a most efficient way. We also use parallel computing based on mesh partitioning. And what is more specific to forging of large deformation processes is the fact that we have very large deformations that require a lot of remeshing. And for instance, for some simulation, we have hundreds of remeshing. So this requires a very robust remesher, which is based on topological improvement, which was developed by Thierry Coupez. And it has also to be done in parallel, so by each core doing its own remeshing, and then we alternate iteratively remeshing and mesh partitioning. Okay, so this was the very skeleton of the software that we are using, and now we see what we can do to try to reduce the computational time for the problem I've introduced. So first, we can look at the incremental process, the problem of cogging, where we have a very large number of strokes, several hundreds. The computational time is very high. And if you can observe here, if you look at the mechanical deformation, you can see that it is highly localized. However, the temperature has to be computed on the whole domain because temperature evolution is very important for these processes because the change of temperature of the rod is very important to take into account. So somehow there are two scales or two physics to take into account, one which requires a very localized mesh and another one which requires a global mesh. So we can study this problem in a more global frame by considering that we have a domain. On that domain, there are several physics to be solved. So usually we use a single mesh that is supposed to be uniformly refined according to each physics. The principle of the multimesh approach is to have for each physics an optimal mesh that is designed to produce optimal calculation for each of the physics. And then the base mesh is supposed to be the union or of all those meshes. So if we have an incremental coupling, as I've introduced in the beginning, so it means that for any time step, we have to resolve the different physics simultaneously. Then if we apply the multimesh method, then we can split this into three parts. First, we have a projection from the base mesh into the mesh of the particular physics. Then we solve in a most efficient way the system on that physics using an optimal mesh, and then we project back, we interpolate back the results on the mesh. So it's a rather simple idea, but which requires to have good remapping operators to avoid losing information during those operations. Those operations that has to be done also in parallel. So the different tricks that we have introduced in order that this method function, first is to design the basic mesh that should be uniformly refined for all the different physics, and then to construct the physical mesh by the refinement of all those meshes. Another trick that can be introduced is to use embed meshes so that the elements are the same. All the elements of the physical mesh also belong to the basic mesh. This makes it possible to have exact transfer when we consider nodal values. Okay, so for the nodal values, the transfer is exact, and then we have a problem of remapping for the values at the integration point. So in our case, we have a linear element, so we have only one integration point per element. So we have P0 operators, so for instance, the stress, the strains. And so there are piecewise elements, and if we do a projection or remapping, there is a lot of loss of information. In order to avoid that, the basic idea is to try to increase the level of information on the current mesh by trying to have more information, to have a higher order field to be transferred. So if we have a P0 discontinuous field, we are going to transfer it into a continuous field using recovery techniques through using the same interpolation functions as we have for the other field. So the basic idea is rather classical. It is based on superconvergent patch recovery, which has been initially developed for error estimators and also used for remapping. So we try to compute a new field, the recovered field, as a function defined from the finite element function, and so the problem is to compute the value at the node, considering a patch and defining a first-order linearization, linear field and continuous field on that patch. this field is such that it is equal to the original finite element field at the integration point. So then we compute the coefficient by least square formulation, and we end up with the coefficient of the interpolation. So this is very classical, but for forming processes, most of the phenomena are taking place on the surface. And when we use this method, the matrix is not defined, the least square method is not defined on the surface. So it is necessary to find a trick to compute that matrix. And this trick should work in parallel and should try to preserve the superconvergence property. So what we have been doing is just noticing that for the nodes that belong to the volume, there is no difficulty to compute the value, this recovered value at that node. So we can add those nodes to the surface patches in order to increase, to have more information using an iterative approach. So in the first approach, we compute only volume node, and in the second or third or fourth iteration, then we can compute the surface node by introducing those values into our least square functional as a regularization function. So very briefly, I just want to show you that with some analytical function, we can actually see that the superconvergent approach makes it possible to have a higher convergence rate, and this higher convergence rate is also observed on the surface, which is expected and very important for forming processes. Okay, so this makes it possible to apply it to our original problem of cogging. So in that case, we have only two meshes, a thermal mesh, which is uniformly refined, and a mechanical mesh, which is refined under the die. And the base mesh is equal to the thermal mesh. So first, we can see that we apply this to a rather complex problem, which is called picturing process. So it's like a rolling, but with it's a rather complex rolling with a complex history, and we can see here, if we look at the stress field, that we have a good agreement between the multimesh method and the reference method, so showing that the remapping techniques is working properly. So, but the main interest was to apply this to cogging, and so for this kind of process, we can see that we can have, so previously we had a speedup up to 6, and we applied to cogging that we have a speedup that can be a 20 and sometimes more. So it's a good method to solve this kind of problem. However, most of the time we cannot use this kind of tricks, so there is no particularity to our problem to take into account. So in that case, what we can do is we can just consider that 70 to 80% of the time is dedicated to solving linear system. So it is very important to have an efficient solver. In our case, the complexity of our solver is n to the power 1.5. So this means that we have a number of iterations which is about n to the power 0.5. So this means that whatever the number of processors we are using, we will not decrease that number. This number of iterations will go on increasing with the number of nodes. So our aim, on the one hand, is to reduce the complexity of this solver and hopefully also to decrease the computational cost. So the idea is to use a multi-grid method. We're using different grids, makes it possible to more efficiently compute low frequencies of the solution. So you see that, in fact, in order to construct multi-grid, we face the same kind of approach where we have different meshes on the same domain, a fine grid and a coarse grid, and then we have to interpolate between these two grids. So the basic of the multi-grid method is we have an iterative we do some iteration on the iterative solver on the fine grid, and we project the solution on the coarse grid where we solve the coarse grid equations, and then we prolongate the correction on the fine grid, and then we do some further iterations. For our problem, we have to apply this to our particular equation that I've introduced in the beginning. And so what we observed is that first we use multi-grid as a preconditioner. It seems to be more efficient. And then we have to consider the fact that in metal forming, contact is very important. And in order to have a good efficiency of the method, it is very important that the coarse grid equation should be consistent with the fine grid equation, and more particularly regarding contact and incompressibility. So this drove us to use an algebraic approach where the coarse grid system matrix is derived by projection from the fine grid. And in order also to have a good efficiency, we are using a geometric approach to construct the different levels of grids in order to have more efficient. So of course this requires to be done in parallel, as has been presented for the multimesh method, and it also requires building coarse meshes that properly represent the geometry, the global geometry of the shape. So some robustness for the remesher. So these are the details of the tuning of the parameters for the multigrid method, and what is interesting to show is just here you have an example of upsetting, and what we see that if we look at the asymptotic convergence of the method, asymptotic cost, we see that for the standard method we recover the factor 1.5 that we had theoretically, and for the multigrid method we have something which is less than 1.1, so it is not exactly proportional to 1, but it's close to n log n, so it is quite interesting. So we can apply it to more complex problems, so reducer rolling or radial forging with different size of problem. You can see that we have the decreasing, using the multigrid methods, we have the decrease on the computational time for solving the linear system, but there is some costs that are not affected by the linear system, so in the end we have a speed up which is about 1.6. This is quite interesting when we have problems that last for several days. Okay, so there is another family of problems for which we can develop some numerical methods to reduce computational time, is what I would call quasi-steady problems. So this is a case of rolling. When you do rolling, most of the time you have the beginning of rolling, you start rolling your sheet, and then you have the end of rolling. And most of the time we are mainly interested by the quasi-steady state of the process. So we can reduce the computational time by reducing the computational domain and by just studying what occurs between the rolls. So in order to do that, we can use the arbitrary Lagrangian Eulerian formulation, which means that the mesh velocity is not equal to the material velocity. So we are using the splitting of the operators. So we have 3 steps. We have a Lagrangian step where we compute the mechanical equation, mechanical thermal equation. Then we have mesh regularization, and then we have remapping. So for the problem we are handling, the main difficulty concerns mesh regularization, because we have complex shapes, and the problem is to perfectly keep the volume and control the shape. So for that, we are using a barycentering algorithm. So for volumic node, it is very simple, but the difficulty arises when we have to deal with the surface. So the surface is known from the deformation, the Lagrangian deformation of the mesh, and the mesh, so the elements are linear. So by projecting a node on a linear surface, there is a lot of diffusion and a lot of errors. So this means that in order to reduce that diffusion, what we are using higher order element. So the idea is quite similar to the one that we have used with the recovery techniques, is before doing the interpolation, we are increasing the quality of the solution on the reference, we want to transfer. So in order to do that, we first compute the normals at the nodes. So the normals are known at the center of the facet, but they are not known at the node. For that, we use a nodal vector voting approach, which has been developed in computer vision, which basically consists in doing some kind of averaging of the value of the different facets from a neighboring facet using a certain weight. So this provides normals very accurately. And from those normals, then we can try to add new nodes on the mid-side segment and to obtain a second order, a quadratic surface, a quadratic triangle, by fitting the position of the node in order to recover the normal that have been defined at the external nodes. So by just adding, so we have a C0 P1 surface, and we obtain a quasi C1 surface, which is P0. So this is applied, has been applied to a large number of processes, but just for rolling, we can see that with the highly formulation, we can decrease the computational time by a factor of 2. And if we have a complex tool stack, then we can have further optimizations, and then we have a most important speed-up ratio. However, I would say that the highly formulation is not the best adaptive for this kind of processes, and is better suited to have accurate simulation for some processes by introducing adaptivity based on error estimation, and to control the barycentering in the barycentering to take care of the element size. So, okay. There's a problem. Okay, so here we can see here that the for instance, if we consider metal cutting, high-speed metal cutting, the highly adaptive highly formulation makes it possible to automatically localize the band, the shear band, and so to have a very fast convergence of the finite element solution. And for instance, here you can see that the evolution of the bandwidth does not depend, the bandwidth does not depend on the size of the element. So it provides a very good solution. Because if we have a steady process as we have in rolling, then this is not the most efficient approach. As you can see here, in fact, in the arbitrary Lagrangian formulation, the look for the steady state is always an incremental process where we have to propagate the information towards the end. So in order to do that, it's more efficient to use a direct resolution of the steady state. This kind of problem has been addressed in the past years, where computer resources were not what they are today by large, but nowadays it seems that there is less activity in that field. So there is a need to adjust those methods to the more modern techniques. Let's speak about unstructured meshes and parallel computing. So in that field, it means that the different approaches that have been developed in the past, not all of them can apply to these constraints. So we end up with a multifield formulation. So by writing the equation for the steady state equation, we have different variables, but all these variables are coupled. So we have the position, but also the velocity, the stress, the strain, and temperature, and there is a strong coupling between all those equations. They could be solved simultaneously using different approaches that can be found in the literature, but as we are using a simple element, linear element, it's, we have too many, this would bring too many degrees of freedom per node, and then we will lose the interest of such approach. So this means that in our case, we are going to solve these different equations in an iterative way using a fixed point algorithm. So the basic idea is we start with a known domain. On that domain, we solve the different equations, mechanical, thermal, and maybe state variable integration. And once we have the velocity field, then we suppose that the velocity field is known, and then we update the free surface. So the equation for the mechanical equation are recalled here and are the same as the one I have shown in the introduction. So the problem regards the free surface equation. So we have, and this is the original surface, this is a new surface, and T is a correction, because now we do not have time. The time has disappeared from the equation. So the velocity field can be assumed to be known and be the same on the default, original and updated configuration. And we are looking for correction which should be such that the normal on the deformed configuration should be perpendicular to the velocity field, which is a free surface condition. Of course, we also have to satisfy the non-penetration condition. Okay, so in order to, the weak form from that equation can be, we can use a Galerkin approach, but we can very quickly see that in fact this problem is a convection problem, is very similar to a convection problem, so we need to introduce some upwind skin. So we use a supg formulation, so with the supg term here in that weak form. And the second difficulty that we encounter is, for instance, if we have a shape like this, and if we want to move it to this different shape, you can easily understand that here you need to have 2 degrees of freedom to come from that position to that position. Okay? So there is a need to introduce 2 degrees of freedom on the edges. So in order to do that, we can use the same techniques that I've introduced previously to compute the normal at the nodes, and for edges we end up with 2 normals. And so for each normal, when we consider the supg function, we shall define the facets that are associated to that normal, and so we shall end up with 2 sets of equations with the supg formulation in order to have enough equation. Okay, for the free surface term, we keep also 2 degrees of freedom, and so we have, and the second degree of freedom, we introduce some regularization of the mesh term. So this is applied to the problem of multipass rolling, Cox rolling, where you see you have 5 passes. You can see the evolution of the bar during the process. This is the iteration. Here you can see the iteration of the fixed point algorithm. You can see the evolution. This is the evolution of contact during the problem. And what we can notice here is that with that steady state approach that we have a rather small number of iterations, 16, which is quite small as compared to the number of increments that are necessary with the incremental approach. And then we look at the computational time, we see that we have a speed up, a difference which is about 60, which properly corresponds to what we are expecting. Okay, so let's come to some conclusions. So what we have observed is that depending on the kind of processes, we have different strategies to try to reduce computational time. If the problem is multi-physics nature, then we can use the multimesh approach, which is very efficient. We have speedups, and we can reduce computational time to what we are expecting. If we have a quasi-steady process, then the ILE formulation works properly, but for me, it's rather a method that is useful to do simulation of more complex processes, like friction stir welding, for instance. And it's better to move toward a steady-state formulation where we have a speed up much more important. However, for the future work, we need to extend that formulation to elastoplasticity, where there were more stronger coupling. And when there are no hypotheses that can be done, then we can use enhanced preconditional like multigrid in order to speed up the computation. And one important result is that the complexity is proportional to n, which means that we can move toward the problem of higher dimensions. So all this work is based on parallel mesh, on the techniques on parallel meshing, on accurate remapping. We just end this presentation by saying that we have not solved all the problems. There are still some problems that resist the analysis. So this is a simple problem. This is ring rolling. And if we are using an implicit formulation, even if we have an adapted mesh, if we are using an arbitrary Lagrangian Eulerian formulation, we are using parallel computation, we still end up with a huge computational time due to the fact that we have a very large number of time increments. So this is still a problem that we would like to solve. And regarding the possibility to go further to what I have presented, there might be a different direction, but one direction that could be interesting is to use model reduction. But model reduction can be used in the frame of reanalysis and optimization. You can see here some preliminary results for the budging of the sheet, where we can reduce by very huge factors the number of degrees of freedom. However, there are some challenges to solve remeshing, handle remeshing, and to handle the problem of contact. Thank you for your kind attention.